Okay, let's start. Thank you, everyone, and welcome to another chapter of the TypeScript course organizing by the ICP.Hub North America and also hosted by Demergent Labs, by Jordan Last, the CEO of, and founder of Demergent Labs. TypeScript course, we are trying to connect with developers and also encourage them and teach them to build on the internet computer blockchain. This is like a beginner course, but also for experienced developers, I think is really, really important to refresh different concepts. The course is based in the Azle book. Today we will discuss, or Jordan will teach about the chapters number 15th, Management Canister, 16th, Canister Lifecycle, 17th, Timers, 18 Cycles, 19 Kavits, and then the 20 reference. Not sure, Jordan, if we have enough time to finish all the chapters. But also, Jordan, we will have or leave the last session for the new updates for the Azle 0.18. Yeah, I think we can start now. Thank you, everyone, again for your time. This is the tomorrow will be the last session, same time, 6 p.m. PST. Yes, all yours, Jordan. Thank you so much.
Okay. I need to share.
Yes. Yeah, you can now.
Okay. Okay. Yeah, basically we're going to finish up the rest of the book today. Because we are releasing the next version of Azle. The goal is to have it fully released by tomorrow night. And what I would like to do tomorrow is to just show you the new release, show you the new syntax, and show you how all these concepts generally work. Now that we've gone over all the concepts, you're going to use all the same concepts just in a slightly different syntax. So I think that would be a good use of time tomorrow. So I mean, it's not too crazy to finish the rest of this tonight. So first is chapter 15. This is called the management canister. And yes, these chapters at the end are still a little bit sparse. I think I mentioned that before. So we don't have them fully fleshed out, but I can go into much more detail in person right now. So the management canister, this is a special virtual canister. It doesn't actually exist. It's not like someone actually deployed it, but it is a virtual canister that basically all other canisters have access to. It has a lot of functionality attached to it. And if you go to the reference section, chapter 20, under management canister, you can see many, if not all, of the APIs that the management canister has available to you. I think there's one missing called canister information or something that we've just added and will be in Azle 0.18.0. But these are basically, this is where you're going to find a lot of system functionality. Anything, I guess, asynchronous, or a lot of just the cool things that the internet computer system is going to be able to do for you, you're going to find here. So I believe we talked about HTTP request already, right? This is one of the key, very nice system APIs that's available. We talked about that previously. And there's a bunch more here. Let's do two things. Let's show like the most basic example of interacting with the management canister in two different ways. I'll show you the really nice abstraction we have, and then I'll show you under the hood how you could do it manually if you had to. So first, what we're going to do is we're going to just create an update function. And all it's going to do is return a blob. Remember, a blob under the hood is a uint array. I'm going to just call it get randomness because we're going to ask the system for some random bytes. And because this is a cross canister call, because the management canister is actually asynchronous. Okay, now I'm going to import a variable that already exists called the management canister from Azle / canisters / management. And I'm going to basically just call the management canister like I would call anything else. In this case, we're going to use the raw rand function, and we're going to call. This will return a call result. If it's okay, it will be a blob with random bytes. If not, it'll be an error. So if actually, I figured something out crazy. Oh, it still doesn't work. Okay, Azle 0.18 does something different with that. So anyways, we'll just check if the error is not undefined. Then we will just trap with the error. Also import IC. Otherwise, we'll return result that okay. Okay. So we'll just go deploy that. Oh, sorry, I probably need to zoom in for you. Okay, so this is the absolute simplest way to get access to the management canister. You simply import this already loaded variable from Azle, basically. Has all the methods on it, and you can just call it and get your stuff back. Okay, nothing crazy. EFX canister call. I just called this example async await, and I'll call get randomness on it. Okay, random bytes from the randomness generation capabilities of the Internet computer. Quite robust, actually. Okay, now let's actually dig into what is actually going on here. So we talked in a previous episode about cross canister calls, right? The management canister itself is simply a service. And all we did was we pre-populated all the types for you. So raw rand in particular, right here, it's an update. It's called raw rand. It takes no parameters, and it returns a call result that has a blob. So this management canister class, which is a service, no different than any other services that you'll make. We created all the types. Here's all the types, and we just kind of pre-populated it for you. So if you're ever missing types, like if Azle doesn't give you a type or something, you can always create it yourself. And then finally, we actually loaded up the variable down here by creating a new instance of the management canister. This is the management canister's principal in string form, 5As-AA. If you just use that, then you can always get to the management canister. So we did all that for you, so that's really easy. Another way to talk to the management canister is to make a raw asynchronous request to the management canister. The IC object has a method called call raw. This allows you to, instead of creating like a service class and actually specifying all of the exact signatures of every method, if you just want to deal in bytes, right? If you just want to encode everything into Candid bytes, send it off, get everything back in Candid bytes and deal with it manually, you might want to do this for dynamic reasons, like if you don't have the types available to you, or if you're, I don't know, proxying stuff or things like that, then you could just do call raw. And in this case, you just pass in the canister ID that you want, pass in the method that you want, pass in the arguments and encode them to Candid, and then pass in how many cycles you want to pass with the call, and then you'll get a result. So this function we could make do exactly what we just did. And let's do it. So I'm going to just call this from the command line. With the canister ID, I'm going to pass in 5A's-AA. For the method, I'm going to pass in raw rand. For the args, they'll just be empty candid, basically. And for payment, I'll just put 0. And we should get a string representing the random bytes, basically. Because right here, notice we're going to decode this to a string. Okay, dfx canister call raw, execute call raw. Okay, first parameter is principal. 1, 2, 3, 4, 5. Next is the method raw rand. Next will be the candid args. They'll just be empty. And next is the payment. Okay, so yeah, it's just it's now been turned into a string and returned as a result. But notice we're getting back random bytes. So that's another way to do cross-canister calls, and also that's how you can access the management canister. So nothing too crazy. Now let's go through some of the APIs available to us. So first up here, we have the Bitcoin APIs. The Internet Computer actually has a very, very tight integration with the Bitcoin network. So what you can actually do is from a canister, using the management canister, you can, if you call Bitcoin get balance, you can actually pass an address in, put in the minimum number of confirmations you want, how many blocks you want built on top, basically, and basically test network or the live network. You do have to pay in cycles for this call, so you can tack on cycles, and then you call it. If you do this, you can actually get back from the Bitcoin network the balance of the address that you pass in. So that's nice. You can also get information about current fees so that you can try to calculate an appropriate fee for your transaction. You can get the UTXO set for an address. And finally, you can actually send a transaction. So you'll turn your you'll sign your transaction and you'll basically turn it into bytes, and then you can use Bitcoin send transaction to actually send it directly from your canister to the Bitcoin network, which is very cool. There's basically Bitcoin-like clients or nodes running alongside the replicas of the Internet Computer that allow you to do this. Canister status. Sorry, I should probably zoom in. Sorry. Canister status. Just basically returns a bunch of information about whatever canister you pass in. I don't believe all information is available to all canisters. There is some authorization on this. So let's go look at that type over here. Let's see. Okay, so if we go into here, so canister status will return a canister status result, which has these things in it. One very interesting and important thing is it will actually return the module hash of your WASM module. So this is a way that you can actually verify the source code of an application on the Internet Computer. You take the source code, compile it down into a binary, and take the hash of that binary. Then you can ask the Internet Computer for the hash, and you can compare them. And then you can be relatively certain that the code that you have seen and compiled yourself is the code that's actually running. And then there's other things in here, like the cycle balance. I believe how much, I'm going to guess total storage that this canister is using. And all these things, if you go to the Internet Computer interface spec, yeah, a lot of this is, I don't know, quite nuanced. So you'd have to go to more source material like this to really understand exactly what's going on. Then we have our actual status, which can be running, stopping, or stopped. So stopped would be your canister is basically not executing transactions anymore. Stopping is like a halfway point. Running is just fine. And then the settings, controllers. Controllers are the principals or the accounts that are allowed to push upgrades and do some other operations on the canister. And then we have a few other things. Compute allocation, I believe, is you can reserve a certain amount of computation from the subnet, because the subnet is sharing resources amongst many canisters. And then memory allocation, I believe, is the same thing. And then the freezing threshold is essentially a threshold at which, as you're burning cycles, which we haven't talked about yet, but we will, as you're burning cycles, your canister will basically freeze itself before you completely run out of cycles and get garbage collected by the system. So yeah, that's canister status, information about the canister. Create canister. This allows you to like literally take a WASM binary essentially and create a new canister. Well, so create canister allows you to register a new empty canister with the system, I believe is what it is. Delete canister will allow you to delete a canister from the system. And let me show you here. Install code. This is what lets you, once you've created a canister, take a WASM binary and actually have that be installed or upgraded on the new canister, which is really cool. So this is how you can actually automate the creation of canisters. Like if you have a DAO, for example, that wants to upgrade itself, you could actually create a proposal, upload the binary, and then have the canister actually perform an upgrade on itself or on another canister. Deposit cycles lets you deposit cycles to a canister. I believe the amount here would be how many cycles you're depositing, but I'd have to double check to make sure. ECDSA public key. This one is very nice. This is a threshold ECDSA key pair essentially that is created for you. And you can create basically as many of these as you want. And it allows you to sign Ethereum or other Ethereum, Bitcoin, or any ECDSA application essentially. It lets you sign these type of transactions in a threshold manner. So no one node has access to the entire key pair because it's a threshold protocol. So it's only shares stored on the subnet. HTTP requests we've gone over a bunch of times. Provisional create and provisional top up. We'll skip those. I don't know really what the provisional means, but they're in here. Rubber we've discussed. Sign with ECDSA. That's the other part of the ECDSA protocol. Once you've created a key pair, you can then sign in a threshold manner. Starting your canister. Stopping your canister. Uninstalling code, so basically removing the WASM binary from a canister. And then update settings. All the settings that we looked at. This allows you to change controllers and compute allocation, memory allocation, and freezing threshold. There you go. And over time, the management canister will continue to grow as new functionality comes. For example, the Ethereum functionality, but similar to the Bitcoin functionality. Imagine we'll just have a few more methods added to the management canister. So let me pause there. Any questions about the management canister before we move on? Okay, then we'll move on to chapter 16, the Canister Lifecycle. Basically, what you're looking at is how you can control control functionality as your canister progresses through what we call its life cycle. At least it's what I call it. Similar, if you're familiar with front-end frameworks like React or web components or other things, there is essentially a life cycle that components go through, right? As a component is instantiated, as a component is connected into the DOM, as a component is disconnected from the DOM, things like that. Canister has similar concepts. The first time you deploy a canister, that's basically called initialization. And you can actually hook into that with the init annotation. And on initialization, this function will run. So if you have some state or something that you want to set up only when the canister is first deployed, for example, if you're deploying a token and you want to initialize all balances at that time, then you can put parameters inside of init and you can store all the information. And it only happened the first time that the canister is deployed. Okay, so this is just the first time your code is deployed. Every time after that, pre-upgrade and post-upgrade will run. Pre-upgrade runs on the current state and code of your canister before the upgrade happens. This is before the heap is wiped. It's before the WASM module, the binary is swapped out. Before. Why is this important? Well, your heap is about to get wiped. So all your global variables are going to go away. So if you want to take any of them and store them in stable memory, or I mean, that's the main use case people have, but there might be others that you can think of. But the point is that if you want to hook into functionality right before canister is upgraded, then you'll call this method. Post upgrade is going to run after the heap has been wiped and your code has been changed. So if you did store anything in stable memory here you could get it out of stable memory and write it back into your global variables. So basically, this is when you will serialize all of your values, store them in stable memory, and here's where you would deserialize those values. So let's say you have global variables up here, let db equal something. You might then convert that into bytes, store that in stable memory, and then here, grab those bytes out, and then write the information back into your global variables. Generally speaking, though, you hopefully will not have to do this. That's what stable structures are for, right? That's what stable B tree map is making it so that you do not need to use pre and post upgrade to serialize and deserialize everything. It's in real time, stable B tree map writes into stable memory. But you might find other uses for these things. And that is the canister lifecycle. I mean, these are just functions that run at these different points. Any questions on the canister lifecycle before we move on to chapter 17? Okay, chapter 17 is all about timers. These are really cool. This set of APIs is going to let you do basically cron job-like things, right? If you want some code to run in the future, it's very similar to the set timeout and set interval APIs in JavaScript. Very, very, very similar. So let's actually we'll go use our async await example. We'll make a simple timer. Okay. So we'll make an update function. Grab IC. Let's test our timer. Let's return void. Okay, here we go. IC dot set timer takes 2 parameters, a delay in seconds. So let's just do for now 1 second as a big int, and then the callback that you want. Okay, I mean, it's extremely simple, right? This function is going to be called one time, 1 second in the future. And we should see that log over here. Once we call it. Huh? Yeah, the timer is running. Very cool. Every time we call this, it will run. Okay, very similar to set timeout, right, in JavaScript. If you want this to run continuously every 1 second, then you would do set timer interval. Yep. So now over here, notice this logged only twice, and we should see it running every second from here on out. Very nice. Okay, let's say you want to, stop a timer once it's going. So let's start our timer here. And let's stop our timer here. Okay, turns out calling set timer interval and calling set timer will return a timer ID that will allow you to cancel the timer. So we'll just store the ID here. Then you can say ic.clearTimer, and we can clear it here. Okay, so also when you deploy, your timer will be wiped. So notice this is going, but as soon as the upgrade completes, the timer is going to be stopped. Okay, the timer stopped. Okay, we'll start the timer again. Oh yeah, we'll call it a different thing.
Ishika.
Okay. The timer is running.
Good.
Are you busy right now?
No, I was.
Oh. Okay, timer's running. And then if we want to stop it, we should have stored it right globally. And so we'll call stop timer. And now our timer stopped. Yay. So those are the basics of the timer API. Very, very similar to JavaScript. So timeout, you can set one timer. In the future, you can set an interval, and then you can clear them. If you upgrade, it'll be cleared. All your timers will be cleared. Other than that, though, they should exist until you clear them or until they're executed. Okay, that's the timers API. Any questions about that? Okay. Basically, the final chapter is cycles. the information gets very sparse here. So I'll just kind of tell you about this. Most important to you is probably this page here. So on the internet computer, all computation, all network resources are essentially metered and paid for in a unit called cycles. Cycles are created from the ICP token. The protocol will allow you to burn ICP tokens and convert them into cycles. Once you have cycles, you can basically send them to canisters, and your canister maintains a balance of cycles. As you store data, as you run computations, as you perform update calls, as you do network requests, the system is going to basically burn your cycles to be compensated for that. So very similar to Ethereum gas. Obviously, it works differently in certain ways, but that's the general concept. Usually, what you're probably most interested in are the costs for the cycle. So you can actually see for all kinds of different things how much it's going to cost in cycles to do things. So for example, just to create a canister on a 13-node subnet, it would be 100 billion cycles. Now, to get some kind of intuition for cycles, 1 trillion cycles is equal to about $1. It's actually equal to a currency called SDR or XDR, a special drawing right. And that right now is, I don't know, about $1.30 to $1.40. Haven't looked. I looked in like the last week. So somewhere around there. So I usually think a trillion cycles is, I don't know, about $1. And that helps you to understand. So 100 billion cycles would be around 10 cents, if my math is not off. So if you're going to create a canister for the first time, it's going to cost you about 10 cents. And then you can start to see what happens after that. So, for example, for every single update call, you must pay 590,000 cycles. So much, much less than 10 cents. For every 10 instructions executed inside of an update call, that will cost you 4 cycles. Every time you do a cross canister call, there's just a fixed cost of 260 cycles. Plus, you have to pay for the bytes, right? And on. So you can see, however much storage you have in gigabytes per second will cost you this much. Doing HTTPS out calls costs you this much. So you can look here to kind of understand that. If you want to profile your own code, there's an API called the instruction counter or the performance counter. Performance counter 0 goes to the instruction counter. So you can just use instruction counter. Okay. And basically right here, I could just tell you exactly how many instructions, everything from here to here cost. So let's do it. But yeah, you can basically throw these into your code to try to find where your instructions are, and then you can use this information to get costs. So if you're interested in Azle's performance metrics, obviously you can run things yourself. Also, we have generated a bunch of information once I can get to the repo. inside of this primitive ops example, there's a benchmarks markdown file. GitHub's being really slow. All right, let's run this. Okay, check it out. 1, 2, 3. So it cost us 100. Well, it took 105,000 instructions to perform whatever we did here. So 105,000 instructions, what you do is you divide that by 4. Right, we're looking at the cost table here. 10 update instructions execution. So we would, so I divided that by 10 and then multiply that by 4 to get the amount of cycles that took. So 105,868 divided by 10 is about 10,000 times 4. So if I'm not mistaken, 42,000 cycles. 42,000 cycles out of a trillion would tell you about how many US dollars it would cost. So pretty cool. It's quite interesting to be able to see, at the instruction level exactly what's going on and then try to figure out how much that actually costs in US dollars. And yeah, that's cycles. I mean, that's the basic concept. You can go, oh yeah, this is loaded now. So if you are interested in getting into much more detail, I mean, this is just our methodology. It could be wrong, but I think it's instructive. What we did is we took Azle, Motoko, and Rust. Motoko is the language created by Dfinity specifically for the computer. We ran a bunch of benchmarks on them and took the basically average number of WASM instructions it took for each. Then we created some scenarios. Basically using this cost table, we said, okay, imagine a lightly used application that has just as many query calls as it has update calls, has this many bytes per ingress message, this many bytes per update message, storing this many gigabytes, has this many update or query messages per second, this many update messages per second, this many cross-connection calls per second, and this many bytes of the call. That's a lightly used, evenly distributed app amongst query and update calls. And then we said, okay, what if you're lightly used but you have more queries than updates? What if you're lightly used and you have more updates than queries, and on and on? So then the most expensive thing you could think of is a heavily used app that's very update heavy, right? Which is having storing 2 gigabytes of data, 1 query per second, 100 updates per second, 10 cross-connection calls per second, with 2 megabytes of data per cross-connection call. So it's like very heavily used. Okay, then what we did is we ran using this information and the number of instructions. We basically just ran this through and showed how much it's going to cost per year to run this thing. And it's not the easiest to read, but the most lightly used was like $4 for Azle and Motoko, $25, or for Rust and Motoko, $25 for Azle. By the way, this is all Azle pre-18. Azle 0.18, I will show you our preliminary metrics are much better. And then the most heavily used apps are getting up to near $100,000 for Rust and Motoko per year, and $300,000 for Azle. And then you can see the average instruction counts here, and then all the benchmarks with all their instruction counts and how we actually got these numbers. We basically looked at a bunch of different data types and did things with them on the stack or the heap at 1, 10, and 100 iterations and added up. So I don't know, it feels pretty like a pretty robust framework to me, but who knows if there's some fatal flaw that we missed. So that's Azle as it currently is. Let me show you the Azle 0.18 benchmarks though. We are literally about to release this. We are just trying to finish up loose ends. All right, here are the new benchmarks for Azle. Notice we're down to 6 million average instructions, basically, versus the old Azle had 128 million. So quite a large improvement here. And we use the same framework for everything. And check it out. Azle's like barely more expensive now. Very, very close. In the worst case, 100,000 to 92,000. So I think it's about 10 to 20% difference instead of 2 to 4x difference. And you can look at all these things again. Okay. Any questions about cycles? Okay, then we'll move on to the caveats. This is just a chapter to kind of throw all the weird things at you about Azle. Unknown security vulnerabilities. We talked about this in the disclaimer section already. Azle 0.18.0 is no longer using a super experimental JavaScript engine. It's using a much more robust engine. So that part will go away. There's still possibly security vulnerabilities because we haven't done all of our testing and all the things we want to do yet. But I believe we have bumped up the security and robustness. High instruction cycle count. Well, you can see here that we have greatly improved on that in many ways, not in all ways. Candid encoding and decoding is 5 to 7-ish, 5 to 10 times more expensive on Azle 18 versus Azle 17. But hopefully in most cases that doesn't really affect you much. Hopefully it'll be usually a fixed cost per call, maybe 1 to 2 million. And we added it up over like 1 million calls. That would be like $4 more possibly. So hopefully that's not too bad. But if you are using like stable B-tree map and doing, I don't know, a lot of inserts or reads or something, it's possible that that could be much more expensive. Mostly what you'll worry about is hitting the instruction limit, I feel. Because remember, update calls have a 20 billion instruction limit. Query calls have a 5 billion instruction limit. So hitting that limit basically ends the execution of your function, which is, I feel like that's one of the most difficult things to deal with on the computer right now. JavaScript syntax and features. You may encounter various missing JavaScript syntax or features. Yeah, but that is before Azle 0.18.0. You shouldn't be missing. I mean, there should be basically no syntax that you'd be missing unless it's like super, super new, like JavaScript 2022 or 2021 or something. Even then, hopefully our compilers can take care of that. And then features, yeah, for example, we don't have set timeout working yet. there's various host APIs that you might expect from the web environment or the node environment. The internet computer is neither of those environments, so it might not be possible to have those APIs, or we just may not have implemented them yet. So let's keep that in mind. Not all NPM packages work. Azle 0.17, a lot of them break for silly reasons because of the engine. In 0.18, sorry, my dog is scratching his collar. In 0.18, my guess is a lot more packages should work because the engine is more robust and doesn't have weird syntax errors or things. And that's one of our highest priorities next, is to start plugging all the APIs that you might need to have very broad NPM package support. Promises work very well, though they might not have the exact same behavior as V8. So that's just something to keep in mind. And I mean, the engines, I think, all have slightly different promise behavior. Maybe, as in, I think a lot of this is not actually specified in the ECMAScript standard. So yeah, just keep that in mind. And then this doesn't even matter. As of tomorrow, it'll be gone. So those are caveats. And then chapter 20, it's just a reference. So all the APIs basically available to you. You can just go look them up. So if you're looking for some kind of functionality, just check out the reference. And let me highlight a couple things in the reference. One is WASM binary optimization. If you ever see your replica tell you that your binary is too big, or there's some HTTP error that won't let you deploy things, you can always tack on this op level 2 defects.json. There's up to 4 levels. It'll take longer to compile. It'll produce a smaller binary as you go up each level. Plugins are cool. We probably won't release 0.18 with plugin support right away, but it shouldn't be that difficult to get them to work again. But right now, you can basically take Rust code and create a TypeScript interface to it and let people use it. It's a little difficult to do because you have to understand a little bit about the underlying JavaScript engine, but if you are a Rust developer, you can do that, so it is possible. If you want to use environment variables, like set some environment variable during deploy or something, just tack on your environment variables into this env property on your defects.json. Whichever environment variables you want to go from your environment into the canister, and then they'll be available on your process.env object, which I think is pretty cool. And I think that's it to spot. Yeah, just to spot check the reference. So, okay, that basically wraps it up. So, happy to answer questions if you have any. Are you talking, Javier? You're muted.
No, sorry, I was talking with Ishika about the hackathons for next week. No.
Oh, okay.
With the course.
Yep. Anyone questions? Otherwise,
tell us about the hackathon.
Sorry?
Where can we learn about the hackathon?
Yeah, we are planning a couple of hackathons with Jordan in Washington, in University of Washington in Seattle. Dub Hacks is next week, and we will have a few workshops and a hackathon there. And also we are working on the Toronto for the Hack the Valley as well. Is another hackathon that we are preparing. ICP.Hub North America will be in the east and in the west of the United States and Canada. Yeah. If you are there in Toronto or Seattle, please feel free to come in.
Thank you.
Jordan, yeah, maybe if what is your idea for tomorrow's session? You want to do the updates for Hustle, or you want to do like maybe a Q&A session as well, or what is your idea for tomorrow?
Yeah, tomorrow I'll just basically, we're going to release the new version, and I'll just go over the new version, all the new features, how all the syntax works, and sure, we can answer questions or anything. But basically just go over all the major concepts we went over very quickly and just show you how it works in the new version.
Cool, perfect. Okay, if it's not more questions, I think we can wrap it up. At least someone want to say something? No? Okay. Yes, again, all these sessions will be are going to be recorded and posted on the YouTube channel. We have here like normally 8, 10, 15 people joining, but we have like more than 400 people joining in the YouTube from other parts of the world. Just if you have questions or you want to review something, everything is recorded. Feel free to go to the ICP.Hub North America YouTube channel and check it out. Thank you so much, Jordan, for your explanations for everything and all the participants today. And yeah, see you tomorrow in the next session, the last session of the TypeScript course.
Thank you.
Thank you so much, Jordan. That was awesome.
You're welcome. Thank you.
Thank you.
See you guys.
Have a good night, guys.
Thank you.
Bye-bye.
Bye.
Bye.
Bye.